Hello everyone. In today's video, we are going to learn about algorithms and efficiency, especially through two very important topics, searching and sorting. When computers work with data, the data is often unorganized. It may be a list of numbers, names, records, files, products, or messages. If the data is chaotic, the computer needs more time to find what we want. So the main idea of today's lesson is very simple. Computers use algorithms to transform data from chaos to order. Searching helps us find something inside data. Sorting helps us arrange data so that searching becomes faster and more efficient. By the end of this video, you should understand why searching and sorting are fundamental concepts in computer science, data structures, programming, databases, and even artificial intelligence. In this slide, we can clearly see the two main ideas of today's topic. On the left side, we have sorting. Sorting means finding one required element from a large collection of data. For example, if we have thousands of student records and we want to find only one student's ID, that process is sorting. On the right side, we have sorting. Sorting means arranging data in a meaningful order. That order may be ascending order, descending order, alphabetical order, or any other logical structure. Now, the important idea is shown at the bottom of the slide. Fast sorting is almost impossible without structured data. Let us take a simple example. Suppose we have many books in a room, but they are placed randomly everywhere. If someone asks us to find one particular book, we must check many books one by one. That is slow. But if the same books are arranged by title, author, or subject, then we can find the book much faster. This is the relationship between sorting and searching. Sorting creates order. Sorting uses that order to find data faster. So, before we study individual algorithms, we should understand this main principle. Organized data gives faster access. This slide explains linear search. First, let us look at unordered linear search. In the upper part of the slide, we can see a list 60, 1, 88, 45, and so on. The search term is 66. Because the list is unordered, we do not know where 66 could be. It might be at the beginning, in the middle, or at the end. So the algorithm must check every item one by one. This is why it is called the brute force hop. It simply jumps from one element to the next element and checks each value. The worst case time complexity is O(n). That means if there are n items, in the worst case, the algorithm may check all n items. Now let us look at the lower part, ordered linear search. Here the list is sorted 2, 3, 4, 6, 7. The search term is 5. We start from the beginning. We check 2. It is not 5, then 3, then 4, then we reach 6. Now, because the list is sorted, once we reach 6, we know that 5 cannot appear after 6. So we can stop immediately. This is called early exit optimization. So in an unordered list, linear search must continue until the item is found or the list ends. But in an ordered list, we can stop early if the current item becomes greater than the search term. However, even with this improvement, the worst case time complexity is still O(n). Now we move to binary search, which is much faster than linear search. The example on the left side is very helpful. Imagine a 1000 page book. If we want to find page 250, we do not start from page 1 and turn every page one by one. That would be like linear search. Instead, we open the book around the middle, near page 500. Then we immediately know that page 250 is not on the right side. It must be on the left side. So we ignore the right half completely. Then we again divide the remaining part. We continue this process until we reach the required page. This is the main idea of binary search, divide and conquer. On the right side, we have a sorted array 10, 30, 100, 120, and 500. Binary search first looks at the middle value. To find the middle value, we use the first index and last index. The midpoint is calculated as first index plus last index divided by 2. After finding the middle value, the algorithm compares it with the search value. If the search value is equal to the middle value, the search is finished. If the search value is smaller than the middle value, the algorithm ignores the right half. If the search value is larger than the middle value, the algorithm ignores the left half. The most important point is shown in the yellow box. The search space reduces by exactly 50% on every iteration. That is why binary search is very efficient. Instead of checking every item, it removes half of the remaining data each time. But one condition is very important. Binary search works only when the data is already sorted. This slide explains interpolation search. Interpolation search is similar to binary search, but it uses a more intelligent guess. Binary search always checks the exact middle of the list. It does not care whether the target value is likely to be near the beginning, middle, or end. But interpolation search tries to estimate the position of the target value based on the value distribution. For example, suppose we have a sorted list from 1 to 1000 and we are searching for 900. A human will not normally start exactly in the middle. We naturally guess that 900 is probably closer to the right side. That is why this slide calls interpolation search the educated guess. On the left side, binary search uses a strict midpoint. It divides the search space exactly in half. On the right side, interpolation search uses an elastic midpoint. The midpoint can move closer to the expected location of the target value. The formula at the bottom uses the lower bound, upper bound list values and search value to calculate this estimated position. So the main difference is this: binary search asks what is actually in the middle, but interpolation search asks where is the target value likely to be. When the data is evenly distributed, interpolation search can be extremely fast, but if the data is not evenly distributed, its performance may not always be better. And just like binary search, interpolation search also requires sorted data. This slide summarizes the searching algorithms. We have three search methods: linear search, binary search, and interpolation search. Linear search has worst case time ON and best case time ON1. The best case happens when the target value is found at the first position. Its mental model is the brute force hop and it has no prerequisite. It can work on unsorted data. Binary search has worst case time ON log n and best case time ON1. Its mental model is perfect halves because it cuts the search space in half every time, but its prerequisite is a sorted array. Interpolation search has worst case or average ideal performance shown as O log n in the slide and best case time ON1. Its mental model is the educated guess. Like binary search, it also requires a sorted array. The catch is shown clearly on the right side. To search at warp speed, the data must be perfectly ordered. So this slide teaches us one very important lesson: advanced searching needs structured data. And that takes us directly to the next topic: sorting. This slide is very important because it connects searching with sorting. Until now, we have seen that binary search and interpolation search are much faster than linear search. But both of them have one important condition: the data must be sorted. This slide says order is never free. That means structured data does not appear automatically. We have to create that structure, and the process of creating that structure is called sorting. Look at the visual on the slide. On the left side, the data is chaotic. The blocks are not arranged. Then the data passes through a machine like process. That machine represents sorting. Finally, on the right side, the data becomes organized. So sorting is like preparing the data for faster future access. However, sorting also takes time. That is why we need to choose algorithms carefully. If we need to search only one time, sorting first may not always be necessary. But if we need to search many times, sorting becomes very useful. This is why sorting and searching are always studied together in data structures and algorithms. This slide explains bubble sort. Bubble sort is one of the easiest sorting algorithms to understand. The main idea is to compare two adjacent elements and swap them if they are in the wrong order. In the example, we have 3, 2, 1. First, 3 and 2 are compared. Since 3 is greater than 2, they are swapped. Now the list becomes 2, 3, 1. Next, 3 and 1 are compared. Again, 3 is greater than 1, so they are swapped. Now the list becomes 2, 1, 3. After this pass, the largest value 3 has moved to the last position. That is why we say the heaviest or largest element bubbles up to the last position. The mechanism shown in the slide uses a temporary variable. First, one value is stored in temp, then the second value is moved. Finally, the temp value is placed in the second position. Bubble sort is conceptually important because it clearly teaches comparison and swapping, but it is functionally inefficient. Its worst case time complexity is O n quadratic. So, bubble sort is good for learning the concept, but it is not suitable for large data sets. Now we move to insertion sort. The slide calls it the expanding wall. This is a very good way to understand insertion sort. The list is divided into two parts: a sorted part and an unsorted part. At the beginning, we assume the first element is already sorted. Then we take the next element from the unsorted part and insert it into the correct position in the sorted part. In the slide, we can see the values 5, 1, 100, 2, and 10. At first, 5 is considered sorted, then 1 is selected. Since 1 is smaller than 5, 5 slides backward and 1 is inserted before 5. Now the sorted part becomes 1 and 5. The search index moves backward to find the correct position for the selected value. This is similar to arranging cards in your hand. When you receive a new card, you compare it with the cards already arranged and insert it in the correct place. Insertion sort has an in-place memory footprint, so it does not need extra large memory. It is also stable, which means equal elements keep their original relative order. Its worst case time complexity is O(n) quantity, but its best case time is O(n) when the data is already sorted or nearly sorted. This slide explains selection sort. Selection sort works by repeatedly finding the smallest element from the unsorted part and placing it in the correct position. The process is shown clearly on the right side. Step 1, scan the unsorted remainder. Step 2, find the absolute minimum. Step 3, swap it instantly with index I. For example, if the list is 5 to 65 10, the algorithm compares values and finds that 2 is the smallest. Then it swaps 2 with 5. After the first pass, the smallest value is placed at the beginning. Then the algorithm moves to the next position and repeats the same process with the remaining unsorted part. The important warning is shown in the red box, predictably slow. Selection sort has both best case and worst case time complexity of O(n) quadrate. Why? Because even if the list is already sorted, selection sort still scans the remaining list every time to find the minimum. So selection sort is simple and easy to understand, but it is not efficient for large datasets. Now we come to quicksort, one of the most important sorting algorithms. This slide explains the first major idea in quicksort, partitioning. In the example, the list is 43, 377, 89, 4 and 20. The first value, 43, is selected as the pivot. A pivot is a reference value. The goal is to rearrange the list so that smaller values go to one side of the pivot and larger values go to the other side. Here the algorithm uses two pointers. One pointer searches from the left side for an element greater than the pivot. Another pointer searches from the right side for an element less than the pivot. If both pointers find values that are on the wrong side, those values are swapped. For example, if a large value is found on the left side but it should be on the right, and a small value is found on the right side but it should be on the left, then the algorithm exchanges them. This process continues until the two pointers cross each other. After the partitioning process, the pivot is placed in its correct position. At this stage, the full array may not be completely sorted, but the pivot is in the correct place. All smaller elements are on one side and all larger elements are on the other side. That is the key idea of quicksort. It does not sort everything at once. It first organizes the data around a pivot and then it repeats the same process. This slide explains the recursive nature of quicksort. After partitioning, we get three parts: elements less than the pivot, and elements greater than the pivot. The pivot is already in its correct position. Now, quicksort applies the same process again to the left side and the right side. This is called recursion. The algorithm keeps breaking the array into smaller and smaller chunks. Each smaller chunk is partitioned again. Then each even smaller chunk is partitioned again. Eventually, the chunks become so small that they are already sorted. The slide describes this as divide and conquer. Instead of sorting the whole list sequentially, quicksort divides the problem into smaller parts and solves them recursively. That is why quicksort is usually much faster than bubble sort, insertion sort, and selection sort for large datasets. Its average time complexity is O(n) log n, although the worst case can be O(n) quadri if the pivot selection is poor. This slide summarizes the sorting algorithms. Bubble sort uses adjacent swaps. Its base case time can be O(n), but its worst case time is O(n). It works in place. Insertion sort uses the expanding sorted wall. Its base case time is O(n) and its worst case time is O(n). It is also in place. Selection sort uses minimum scanning. Its base case and worst case times are both O(n). It is predictably slow because it scans the remaining list every time. Quicksort uses recursive partitioning. Its base case time is O(n) log n and its worst case time is O(n) contrary. It uses minimal memory and is generally very efficient. The conclusion on the right side is important. Selection sort is predictably slow. Quicksort represents the peak of optimized array manipulation through divide and conquer recursion. So this matrix helps us compare not only what each algorithm does, but also how much computational cost each algorithm requires. This final slide gives us the complete blueprint of the lesson. We start with raw chaotic data. This is data without any useful order. It may be random numbers, names, records, or files. Then the data enters the forge. The forge represents sorting algorithms. In this slide, examples include insertion sort and quicksort. After sorting, the data becomes structured data. This means the data is now arranged in a meaningful order. Once the data is structured, searching becomes much easier. We can now use faster search algorithms such as binary search and interpolation search. Finally, the goal is fast retrieval. In real world systems, we always want to retrieve information as quickly as possible. The final sentence is the main message of the whole presentation. Structure dictates speed. Master the sort to conquer the search. This means that the speed of searching depends strongly on the structure of the data. In databases, search engines, artificial intelligence systems, recommendation systems, and normal applications, this principle is used everywhere. If data is unorganized, the system becomes slow. If data is well structured, the system becomes fast and efficient. So, searching and sorting are not just basic programming topics, they are the foundation of efficient computing.